Hello, I'm Evan. I'll be going through questions 7 and 8 on the homework. So for this one, for the first part, we want to find the speed at this point in between when it first enters this straightaway. So we'll start that by getting the displacement. And so we already know this 100, that's given. But then we need to find the displacement along this curve. And the way I did that was looking at the circumference of a circle, which is 2 pi r. But then because we only have like this quarter, it becomes pi over 2r. And so solving that out with this given radius, we'll get 335.6 meters, which I'm going to end up rounding for just so it's easier. So we have the given speed at the end, as well as we know it starts at 0, and the displacement. So we have 3 givens, which we can then plug into any kinematic equation. I started by solving for acceleration, which will turn out to 0.65 meters squared. I should have squared this, that's my bad. Once we have that, we can then solve for velocity, which will come out to this is just a different kinematic equation. This will solve for 17.45 meters per second, which is going to convert to, I believe that is, it's a 62.83 kilometers an hour. And then...
So you converted everything to meters and seconds, and then you converted
Yeah, I don't think we have to do that. It's just like, I feel like every problem is always like meters per second, so I just feel comfortable doing that.
No, I'm the same way. I was just wondering.
Yeah, I don't think you have to do it though, probably not. The next part for question 8, we're looking for acceleration while t is equal to 20. So we will multiply the time by the original acceleration, and that'll get you, I believe that's the tangential, that's the word for it, the tangential acceleration. But then we also need to find the acceleration along this curve, because this wouldn't apply to like a kinematic equation, so we couldn't use the same equations. We'll instead use the centripetal acceleration equation, which is v squared over r. So you plug that in and you get 1.13 meters per second squared. And then to get the total acceleration, you use this formula down here, which is it's essentially using Pythagorean theorem, but with accelerations. That's what I think of it as. So you square them both and then take the square root of their sum, and you'll get 1.3 meters per second squared.
So that's the total acceleration is equal to the normal acceleration and the tangential acceleration.
Add it up and then, yeah.
All right, thank you.
Yeah.
Okay, I'm gonna adjust this. Okay, I don't know if you can see that. We're gonna squat down here. No, it's all right. I think this is good. All right, I'm Andrew. This is gonna be the first 2 problems on the homework. So we're given that there's 2 boats, my lovely drawn boats here, boat A and B. A is a little bit ahead of B already. They're both currently going the same speed. It was given in kilometers per hour, but I've already converted it to meters per second, so they're going 53.3 meters per second. And they both start accelerating at a different rate, and eventually we're given that boat B catches up to boat A. And we know that happens at 8 seconds over here, and we know that boat A is going 62.5 meters per second when that occurs. So using that information, we can plug into the kinematic equation, solve for the acceleration of A, and we're going to get 1.15 meters per second squared. And then since they're going to have the same displacement at this moment in time at t equals 8 seconds, we can set these 2 kinematic equations equal to each other, where this side is going to be corresponding to boat B, and this side is corresponding to boat A. And now we have a single unknown in the equation to solve for the final acceleration of boat B, which is going to be 2.71 meters per second squared. So pretty simple, pretty straightforward, just kinematic equations.
I don't think I did a system of equations like that. I got the right answer, but...
What'd you do?
I think I had used another delta x b that I solved for. I used another...
So you solved for the final velocity of boat B and then plugged that back in?
I think so.
Oh, yeah, I think that would work too.
I think I did a different way than both of you.
Yeah. So there's a lot of different ways because there's 4 different kinematic equations. So I think I don't know if this is the quickest or not. It's just 2, but
quicker than mine. So.
Yeah, it's quicker than
pretty
mine.
simple. So all right, I'll pass on the baton.
Thank you.
Okay, I'm Case. I'll be doing number 9. So in this problem, we have a boat that's traveling with a velocity. It
They
gives
really
it to
like
us.
their boats.
Thank you. Yeah, I know. 9, 10, 1. Damn. And I convert it to meters per second, and then it also gives us an angular velocity of like so there's this guy, kind of, what is that? Parasailing, yeah. And this rope is like increasing its like degree, I guess, per second, which I converted to ratings per second because that's the units we use.
So I was thinking about it like the wind is like pushing him up this way, so he's going like this way.
Yeah, that's why the velocity vector's there.
I like that, yeah.
So using our rotational kinematics equations, we know that V equals RW, and our R is just the length of the rope, which is 200 meters, gives it to us, and our W, or omega. So we get our V, but we want it in terms of like X and Y components, so it also gives us this angle. And then using our X and Y components, we can take the magnitude of the total velocity. So we have the X component of the guy plus the X component of the boat, and that's our X component, and our Y is just what we just solved for. So taking the magnitude of that, we get our velocity, and then to find the angle, we just use those two components again. And then for acceleration now, using the other rotational kinematic equations, we know that it's omega squared r, and we have our omega, we're given r, and we can just find that it's 0.245 meters per second squared at the angle that is given us.
Because we're looking for like that instant in time, I guess you could say.
Yeah. And I think that's it for me.
Yeah, it makes sense.
Is that good?
Yeah.
All right, gang.
Can you see everything?
Yeah.
Okay.
I don't know about you, but I was a little spooked when I first saw this because it's like they give you this picture and you get one value, and you got to find some other values.
It was a pretty scary question.
It was scary, but we worked through it. We got there.
It's actually pretty easy once you got.
It's actually pretty easy once you get going here.
Wow.
So it's kind of similar to one in class. I think she called it dependent motion or something, but we had a pulley problem in class where she set up. She did what I'm about to do. You set up a position, so we have YC plus 2YE is equal to a constant, which you can just derive by.
What is YC?
That's the
that's the Y position
displacement
of the
of
C.
the chord here.
Yeah. Okay.
Great question.
Thank you.
So
I worked hard on that.
So we can take that derivative, we can turn it into velocity equations, and we have this velocity, which is VE. We can plug that in, and we can get -8 meters per second. It's important to note the direction because I think McGraw wanted you to put in the upwards one, so you're gonna have to switch the signs here. And yeah, we essentially do that again for number 4. For number 5, it's a we call this
Mechanical advantage?
no.
Relative motion.
Relative motion.
Relative velocity.
Wait, time out. Before I get there, for these ones, it's important to note that you kind of treat these as separate like systems almost when you're making your equations. So for number 3, we're dealing with the chord C and the mass in the middle. Because this pulley is hooked up like this, we're observing the mechanical advantage of the pulley essentially. So we'll only pay attention to this, not this like other pulley that's connected by this like the hook. Thank you. So yeah, that's important. And that's why we can make these equations, and because if not, then I don't think this would be solvable. So for the relative motion ones, we have. I did it relative. The question asked for this relative first from the chord to the elevator, which VCE is equal to VC minus VE. This is the standard. So the first letter is this, and then the second letter is subtracted from that. Yeah, pretty straightforward. You can do that twice, and you get your answers. Once again, pay attention to the direction and your negatives, but otherwise you're smooth sailing.
All right.
Thank you.
Thank you very much, Thomas. I think that makes sense. I don't know where Case went. He was just here for the discussion.
Or Evan. But